The last part of this energy section, kinetic and gravitational potential energy, part 4, we'll look at a series of examples dealing with everything taken so far and kind of bring it all together. So I'll do a few examples here, 2 or 3, and then we'll see how this all works. So first one, example 1. A 10.0 kilogram mass is released vertically from rest at a height of 60 meters. If the object falls 40 meters down from the maximum height, what is the kinetic energy of the mass as it falls at that point? So, if I didn't give you one, you need to draw one. Draw a little sketch of that. What are we talking about here? So we have an object, lifted it up 60 meters, and then it falls 40 meters. So of course if it's lifted up 60 and falls 40, that means it's 20 off of the ground. So we can take a look at the two scenarios here. What's the before, what's the after? The before is the object is lifted to here, after the object is here. Okay? So we can use what we just looked at. The total energy before is equal to the total energy after. And of course we can break that down into, let's put a little b here for before and a for after and after to distinguish between the two. Kinetic energy before plus gravitational energy before must equal the total after. And of course, you should realize from those other examples that having the object here, this is the before, it's hanging here, it's not moving, so this part here is 0. It's not moving. Okay? When it falls 40 meters, it's off the ground, so it's going to have potential. And chances are it's also moving at that point, so it has kinetic energy as well. So there's this scenario here. So I broke down U into mgh. Now, potential energy before is going to use the height before. Potential energy after is going to use the height after it has fallen down. So that's the key, kind of analyzing the situation and looking at the variables here and figuring out what we know. Now, solving for Ka, I'm going to isolate it. So it's K plus mgh, so subtract mgh. Subtract mgh from each side. And I end up with that. So mghb minus mgha. And what I'm going to do here is something that you would have learned in factoring in math class. We have mg, a common factor. We can factor out that common factor to get mg multiplied by hb, mg multiplied by negative ha. Just making it easier, because now I only have to fill in m and g once instead of twice here. So, working that now, I was told it was a 10 kilogram mass. G is against gravity, 9.8 meters per second squared, that should be. And the height before minus the height after. 60.0 meters minus 20.0 meters. And I get 3,920 technically kilogram meters squared per second squared, but of course that's joules. Okay? The second example I have. Let's take a look at this one. Very similar to that pendulum example I did. A swinging ball with a mass of 1,200 kgs is used to wreck a building. It is raised 4 meters vertically when it is pulled to one side. What is the kinetic energy of the ball just as it strikes the building? Okay, it's very similar to the previous question actually. So once again, a picture is worth 1,000 words here. So I just simply drew kind of the ball being pulled up. Once again, the 4 meter vertical height is from here to here. So the situation before is the ball sitting there. After, it's just about to strike the building. So of course we have energy before compared to energy after. So I use kinetic energy before plus potential energy before equals kinetic energy after plus potential energy after. And of course, same thing as the previous one. We've lifted the wrecking ball up. It's not moving up here. So kinetic energy before is 0. And then after, as it falls, when it's at the lowest part of the path, guess what? It's essentially ground level, so potential energy is zero there. So you have to be able to figure those out. Kinetic energy, so 100% of the energy is potential, 100% of the energy is kinetic as it strikes that wall. So breaking U down into MGH before and height before. Now I'm just asked to find kinetic energy, so I leave this as Ka. Don't have to break it down into 1/2 mv squared. And so we get 1,200 kilograms multiplied by 9.8 meters per second squared, multiplied by 4. And we simply get 47,000 joules. We'll try that on your calculator, make sure you can get that same result there. In the next part, we'll look at a few more examples to bring this into a close, the idea of kinetic potential energy and total energy.